last lecture we saw the scattering cross section. We have derived a formula for the scattering cross section and we expressed it in terms of the matrix elements of the S operator. So, the matrix elements of the S operator gives us the cross section, which is an experimentally measurable quantity. What we would like to express, therefore, once we know the matrix elements of this S operator, we know what the cross section is, and similarly we can derive a formula for the decay rate and so on. All the physically measurable quantities are expressed in terms of the matrix elements of the S operator, or in other words, if we know the S matrix, then we know physically measurable quantities. What we can do is even something which is even better. We can consider the matrix elements of the S operator. We can express them in terms of something which we will call as the endpoint correlation functions or the Green's function. So endpoint functions gives you the S matrix and the S matrix gives you physically measurable quantities. What we will see in today's lecture is, once we have the S matrix elements or a transition amplitude, how can we express this transition amplitude in terms of the Green's function. So this is what goes with the name as the LSZ reduction formula, which is what we will do in this lecture. So to do this, let's consider a theory which is self-interacting. You consider that there are these particle states in the theory. At some t goes to infinity, the particles are t goes to minus infinity, the particles are essentially free. At finite time they come close to each other, they interact, and then again finally there is some output which you measure. So what you do, usually what we would like to do is, we would like to carry out all our computations in the either in the in Hilbert space or in the out Hilbert space. Essentially we know everything about the free field theory. So we would like to express all our computations in terms of the quantities which are free field quantities. That is what we would like to do. So therefore we have the, let us say for example, you have the free field which is phi in of x. This free field generates the in space, the Hilbert space is generated by this field, and all the observables in this free theory are essentially expressed in terms of phi's and various functions of phi, and you compute the matrix elements of those functions. Those are the observables. What you have in practice is the interacting theory, and you want to compute various things in the interacting theory. What you would like to see is how to express various computations in the interacting theory in terms of the computations in the free theory. That is the goal here. So what you do is, you have, suppose you are having a self-interacting theory, you consider the you assume that the interaction takes place at some finite time, but as t goes to minus infinity or t goes to plus infinity, the theory is essentially free. So what you do, you have these interacting terms, and you essentially introduce some adiabatic function in the interacting interacting terms, or in the essential, in the equation of motion you have the couplings, and you introduce an adiabatic function in the couplings, which essentially is 1 at finite time, and this function as t goes to plus infinity or minus infinity, this function goes to 0. So that way at finite time you have this interacting theory, you study the interaction, I mean the particles come close and interact, but as t goes to plus infinity or minus infinity, the theory is essentially free. So, because of this introduction of this adiabatic function, what you essentially land up is, when you suppose phi of x is the interacting field and phi in of x is the free field, then in the limit t goes to minus infinity, this field phi of x goes to phi in of x up to a normalization constant, which I will call as z. So, z to the power half. For convenience, I will introduce this number here, this coefficient here, z to the power half, and the interacting field goes to this at some as t goes to infinity. You might think that you can essentially redefine the normalization and then observe this coefficient in the definition of the field. However, we will see in a moment that that is not true. In fact, this statement is true matrix element wise. So, let us consider the commutation relation of the field phi of x, the interacting field phi of x with phi of y, and compute its vacuum expectation value. We will find a representation for this this quantity, and then from there we will see that this constant z here will be a number which lies between 0 and 1 for the theory to be interacting. So, let us consider this commutator here. This commutator is essentially phi of x, phi of y minus phi y phi what I will do is that I will introduce a complete set of positive energy states here. So, if alpha represents a positive energy state, then I will use the completeness relation and this expression, which is the identity, and I will insert it here as well as here. When I do that, what I will get is that this gives two terms. The first term is written as the first term becomes vacuum expectation value of phi of x sum over alpha I can take the sum outside, and also I will use this relation phi of x equal to e to the power I p dot x phi 0 e to the power minus I p dot x. Then what I have here is this matrix element phi x alpha. This quantity will become 0 e to the power I p dot x phi of 0 e to the power minus I p dot x. Here this acting on the vacuum, this will keep the vacuum invariant, whereas this will give you a factor of e to the power minus I p alpha dot x. So, what you get is this times phi 0. Here you have a alpha alpha. Okay. So, I will use this relation here. You will get a similar expression for the second matrix element, and hence this quantity here becomes sum over alpha e to the power minus I p alpha dot x minus y times 0 phi of 0 alpha and alpha phi 0 0. Okay. So, this is the first term in the commutator. Therefore, the vacuum expectation value of the commutator becomes there is a sum over alpha e to the power minus I p alpha dot x minus y. Then because of the commutator you have minus e to the power I p alpha dot x minus y times this quantity here, which is mod 0 phi of 0 alpha square. This is what we get for the vacuum expectation value of commutator of two fields in the interacting theory. What we would like to do is, we would like to express this quantity in terms of the vacuum expectation value of commutators in the free field theory. That is what we would like to do. To do that, let us write it in a form that will be more convenient for us. Let us introduce this identity operator, which is integration d4 q e to the power delta of q minus p alpha, the 4-dimensional delta function, is equal to 1. Of course, this is a trivial identity, it follows from the definition of delta function. I will use this is true for any value of p alpha. So, I will use this here, and when I do that, what I will get for the commutator is this is equal to integration d4 q delta I can introduce it in each term. So, this is sum over alpha integration d4 q delta of q minus p alpha mod of phi of 0 alpha mod square times e to the power minus I p alpha dot x minus y minus e to the power I p alpha dot x minus y. You will see in a moment why I did that. This quantity does not depend on q. So, I can just pull out of this integration. So, this is on the other hand, here because of the delta function, what I can do is I can replace here instead of P alpha, I can write here as Q. So, what I get here is integration d4 Q sum over alpha delta Q minus P alpha phi 0 alpha mod square, and here you have e to the power minus I q dot x minus y minus e to the power I q dot x minus y. You can see that trivially if you start from this step, because of the delta function here you get the step. Now, the only alpha dependence comes in this term here. So, it is already summed over alpha. I will introduce a function rho of q, which is known as the spectral function. Rho of q is summed over alpha delta q minus p alpha vacuum expectation sum the expectation value of phi of 0 alpha mod square. So, once I introduce that, I can see that the commutator vacuum expectation value of the commutator can be written in the following form. So, this quantity is equal to integration d4 q rho of q e to the power minus I q dot x minus y minus e to the power I q dot x minus y. Okay. Now, what is the now you can see why I wanted to write it in this form. This is quite similar to the commutator of two free fields, except this function rho of q here. Instead of rho of q, you had dq over 2 pi cube q 0. That was the commutator of vacuum expectation value of commutator of two free fields. Now, let us look at the function rho of q. This rho of q, first of all, it is because these p alphas are the functions p alphas here have positive, these are positive energy eigenvalues. Therefore, this quantity can be expressed as theta of q 0 times some function sigma of q square here. You can substitute this value of rho of q here, and then you can compare this with the commutator of two free fields, which is phi in of x, phi in of y. This commutator here, which I will also, or the vacuum expectation value of that, which is also denoted as I delta of x minus y. I will use, I will write another, I will label it by m also to make sure that this is a commutator of some free field whose mass is m. This commutator we already know is given by dq q over 2 pi q 2 q 0 times e to the power minus I q dot x minus y minus e to the power I q dot x minus y. So, therefore, it is clear that this commutator here will essentially be superposition of this delta x minus y m, the superposition of commutators of this for various masses. You know the single particle states are stable. So, you have because of the interaction in the theory, you can have I mean the field can create multi-particle states and so on. Let us assume that m1 is some energy scale above which multi-particle states are created. Then you can see that this commutator here will essentially be superposition of these deltas, except that the multi-particle states are created at some energy which is m1. So, this will be I delta. This will be a bunch of sum of these deltas of various masses, except that the lowest one has delta x minus y m, and then you will have, because I am denoting m1 to be the threshold for creation, threshold energy for creation of multi-particle states. So, you can write it as something, you can represent this as integration over d m prime square sigma of m prime square times delta of x minus y m prime, except that because of the normalization condition, because we have introduced this factor z here, phi of x goes to z to the power half phi in of x. Because of that, you will have a factor of z here. So, you have I z times this. This is what you will get for the commutator of these two interacting fields. From this relation, it is clear, right? You can express this as a integration over d4x, and you can compare these two terms to conclude that the vacuum expectation value of the commutator must have a form which is like this. Now, you look at this here, you can see that if you differentiate this with respect to time, and then if you set t equal to 0, okay. So, then if you differentiate it with respect to t, you will see that this q0 factor here will cancel in both these terms, and if you set t equal to 0, then this will become a 3-dimensional integration. Both these terms will be the same. So, therefore, that will also go cancel the factor 2 here. So, you will get a 3-dimensional delta function. So, I del 0 delta x minus y at x 0 equal to 0 is delta x minus y. Okay. This is clear, because this differentiation here, this because of this minus sign here, you will get one minus sign, both these terms add up, and that cancels this factor 2. The differentiation gives you a q 0, that cancels this q 0, and you can make a change of variable here from q to minus q in the second term. All those things make sure that you get a delta function here. So, you can do that. You can consider this term here, differentiate it again with respect to t, and then you will get a delta x minus y here, 3-dimensional delta here, here, here in all these terms. When you do that, you see that this integration here does not, the m dependence goes away. So, if you differentiate this with respect to t and set t equal to 0 and collect the coefficients of delta x minus y, what you will get here is, there is an identity here, 1 is equal to z plus m1 to infinity d m prime square sigma of m prime square. The sigma of m prime square is positive. You can see this from the expression for rho here, which basically is a sum which contains a delta function and mod square of some quantity. Therefore, this is a non-negative quantity. Therefore, this quantity is positive. Hence, you can see that this z here is essentially a number which lies between 0 to 1.
How did we get that identity?
This identity, this one is, you can see that this commutator here. So, you start with this relation, right. Now, you differentiate it with respect to time, and then what you will get is, in each of these terms you will get a delta function, 3-dimensional delta function. You set this time t to some value, let us say you set t equal to 0. It need not be 0, it only the difference has to be 0 here, x minus y here. If you set that to be 0, you get the left hand side here simply becomes delta q of x minus y, and here again you will get a delta q x minus y, this also because of this relation, and same about here, and this basically gives you that this identity holds. So, this is so both the quantities are positive here, this is positive, this is positive, and hence you get this identity, this relation that the constant z lies between 0 to 1. Z equal to 1 means this one is 0 here. So, therefore, the theory has to be essentially a free theory, the field has to be free theory, no multi-particle states are created here. This quantity here, for example 0 to phi. So, this is 0 means what? This quantity has to be 0 for all multi-particle states here, but you do not want, in an interacting theory, you do not want this to be 0 for all multi-particle states. Only in a free theory you have this quantity here, the field phi creates a one particle state out of vacuum. So, in a free theory this is this is non-zero when this is a one particle state, and this quantity is 0 when alpha is a multi-particle state for a free theory. On the other hand, in an interacting theory, you have also you want the interaction to create multi-particle states. Therefore, this is also non-zero when alpha is a multi-particle state. Here I have separated out the single particle state contribution and the multi-particle state contribution. The single particle, so when alpha is a single particle state, you get the first term here, and when alpha is a multi-particle state, you get all the terms here, and this quantity z equal to 1 essentially means that this has to be 0 here, and thus that means that this is 0 when this alpha is a multi-particle state. So, you essentially land up in a free theory. So, to have an interacting theory, you have this z, which is a number which is less than 1. Okay. Any question after this? Now you would like to consider this. So what we have shown so far is phi in the limit t goes to minus infinity, this goes to z to the power half phi n of x. What happens when t goes to plus infinity? Again, you can use the same argument here, and you can because the out state also, I mean the field phi out x is also a free field. Okay. So, all the arguments will hold, except that you do not know whether you get the same coefficient here or you get a different coefficient. So what I claim here is that again when you consider t goes to infinity, phi of x goes to z to the power half phi out of x with the same z. The reason is the following: when you quantize, of course the ground state is unique. So your in vacuum is same as the out vacuum. The single particle states are again stable. So the single particle states are also the same up to overall phase factor, they will be the same. And if you consider quantity like this, the x dependence here and the x dependence in phi in of x 0 phi out 1. So, they have the same functional form here. So, only thing that can differ here is the overall constant, but because both the vacuum here and the single particle states are the same for both in as well as out vacuum, therefore, the multiplication factor here also has to be the same. So, you get the same quantity. Now, with this what we can do is, we can now consider the transition amplitudes. So, let us say some transition amplitude which is also some matrix element of the S matrix, and we will do some manipulation and we will express this quantity in terms of the endpoint correlation functions. So consider some final state which is a P1. When we did the scattering cross section calculation, we have seen that even if we consider wave packets, ultimately the cross section is expressed in terms of some quantity where both these quantities are eigenstates of the momentum. So, you consider P1 up to some Pn out and Q1 up to some Qm in. This is the amplitude that we are interested in. So, let us start with this amplitude. Let us consider the state Q1 to Qm in. This can be written as A in Q1 dagger. This will create a one particle state of momentum Q1. Therefore, this state is equal to Q2 up to Qm in. All right. So, I will use this formula and I will use it m times iteratively, and then finally we will see what we get. So, let us consider the first step, which is P1 here, A in dagger Q1 Q2 up to Qm in. This is what we have. Now, this A in dagger, this I can express in terms of the field phi in of x, right. So, if you go back and check your notes, you can see that this quantity phi A dagger in of Q1 integration dq x times 1 over I e to the power minus I q dot x del 0 phi in of x minus del 0 e to the power minus I q1 x phi in of x. Okay. So, you can substitute this expression here. Remember that although here you have each of these term here depends on t, the t dependence goes away and this is some quantity which is independent of t. So, you can evaluate this integration at any given time, at whatever time you like, you can evaluate that. I will write this quantity as d cube x e to the power minus I q1 dot x del 0 phi in of x. So, I am introducing this notation here to write this derivative here both ways with a minus sign. No. Thank you. There is a 1 over I. So, this is what you have. So, I will introduce this, I will use this, and then what I get here is integration d cube x P1 e to the power minus I q1 dot x 1 over I del 0 phi in of x and then q2 up to phi out. This is in, right? All right. This derivative here acts only on this phi, it does not affect any of these things, and this is a number here. So, I can just pull out all these things, then what I get here is d cube x e to the power minus I q1 dot x 1 over I del 0 Now, since I can evaluate this integration here at any given time, I can evaluate it as t goes to minus infinity. Therefore, this quantity here again is same as itself in the limit t goes to minus infinity. But now what I can do is, now I know in the limit t goes to minus infinity, this phi in is related to the interacting field phi by a factor of z to the power minus half. So, this quantity now is equal to limit t goes to minus infinity z to the power minus half integration d cube x e to the power minus I q1 dot x del 0 here p1 up to pn out phi of x q2 okay. There is a 1 over I. Now, what you can do is, you can consider quite independently, you can consider this quantity here and take the limit t goes to plus infinity. Okay. If you take the limit t goes to plus infinity, what you get here is, instead of phi in, you get phi out, and hence here instead of a in dagger q1, you get a out dagger q1. So, this a out dagger q1, now what it will act is, it will act on this state here and then it will annihilate one state. So, you start with but that is the quantity which is taken in the limit t goes to plus infinity. So, you consider some arbitrary function of t and you consider limit t goes to plus infinity f of t, and you consider limit t goes to minus infinity f of t, you subtract these two terms. What you get here is integration sum ti to tf dt del over del t f of t in the limit t I goes to minus infinity, t f goes to plus infinity. all right. So, what I will do here is I will consider this quantity here. What I have shown here is, if I take this quantity, take the limit t goes to minus infinity, then I obtain t goes to minus infinity z to the power minus half this is P1 a integer right. Now, what I would like to do is that I would like to consider the same quantity limit t goes to plus infinity z to the power minus half dqx e to the power minus I q1 dot x 1 over I del 0 P1 So, when I take the limit t goes to plus infinity, what I have here is P1 out a out dagger q1 q2 up to qm in. But now, if I subtract this term from this term, this limit just goes away. What I get here is an integration over d4x time derivative of this whole quantity here. So, this integration d4x time derivative of this whole quantity here is just the difference of these two terms. So, we will start with this relation in the next lecture, and then we will see that we will get a reduction formula. You can do that. Now, we can start acting this on this state, and we will keep doing that, and then we will get a reduction formula which essentially will express this matrix element that we have started with in terms of the n point correlation functions.